Okay, so this is Spring 2020 Chemistry 2, the last discussion problem set on the organic mechanisms. So we are trying to continue to talk about to have a better understanding about reactivity, and this one is essentially they're trying to give you an idea about consider the leaving group, which is shown up here. So this leaving group will favor SN1 or SN2, right? So this is coming from the understanding that you have to understand that this is a nucleophile substitution reaction, and 1 means unimolecular, and 2 means bimolecular. Okay, so in a way, I can put this in a wording such as this is a bimolecular. What that means is poor leaving group. And if you look at here, this compound has essentially protonated hydroxyl group, and then whereas which is actually good leaving group. So this is actually has something to do with a good leaving group. And the water is a good example as a considered to or hydroxyl group as a good leaving group, because poor leaving group, one example is actually OH. And whereas this one is when OH is being protonated, and let's say I'm just considering this scenario, and when they're trying to leave, make this molecule to leave here, they need to take this 2 electrons and trying to take it, right? By doing so, what's going to happen is this one will result in H2O, which is a neutral. So that's a pretty easy process compared to this one. You need to essentially develop OH minus as a leaving group. This is a leaving group, right? So this is a leaving group. And that's pretty much not likely happen, but this is, so this is, when it's poor, not likely. So therefore, you need something that actually, you need a help, something like attacking from the other side, and that's a nucleophile. Is attacking from the other side, and to cause this reaction. Whereas this one is itself is I'm good to go. So therefore, by losing water here, they can develop this positive charges on the carbocation as a transient structures, and then they can have a nucleophile to be the nucleophile attacking this carbocation to form the bonding. They can go from the top or they can go from the bottom. Right? So it is a way that this is a different mechanism. So this is an SN1 and this is an SN2. And SN2 is implying that you have a poor leaving group or weak leaving group, so that you need someone's help to actually pull and push, right? So this is the motivation to leaving is not so high, so you need an additional help. Whereas this one, SN1, this leaving group itself is sufficiently good enough, because once they leave the bond, they break the bond, and this is a heterolysis, which is you take 2 electrons by the leaving groups, and then you ended up getting this neutral. So neutral is not so bad, right? So identifying this this reaction is a good leaving group. So you therefore you can say that's an SN1. Unimolecular is good enough because they can generate those, and that's a good insight for you to know. So okay, so therefore, if you have a hydroxyl compound and just adding a catalytic amount of the acid, and they can protonate the hydroxy and make it change the hydroxy group into the hydronium, which is so that the H2O plus is a side group, so they can leave this one over there. So I want to actually give this opportunity to actually give a little summary for me to. I want you to share this one to you guys. And this is actually we've been talking about discussing throughout. And then let me just make a little table here. So I want to make a table. And so this is we are using the term. There are essentially pretty much the 4 different categories we've been seeing it. What we call the nucleophile. Right? It is sometimes people just say nu with lone pairs. So this is the one that seeking for something that is positive. That's why they like phile, means they like it. They like nuclear, something that is a partially positive charge. And this is a term that is used for SN types of reaction, right? Nuclear substitution reaction. We call this something with these lone pairs is we call the nucleophile. Whereas something that remember the elimination reaction, and we call this one as actually base. Base, and then they sometimes use this notation here, the base. That's a notation that organic chemists use to represent. And this is a base that's trying to actually take the proton from the carbon adjacent to the compound, and then they at the end, elimination reaction will cause the result in the double bond formation. And there are 2 different types of categories. One is, what about if you're using the strong nucleophile? What about if you're using the weak nucleophile, right? So if you're having the strong nucleophile, then means the nucleophile itself is a good one to kind of push in the reaction. So this one is actually, regardless of about where SN2 reaction, it will be possible. And then the kind of the related portion is, despite you have a poor leaving group. Okay, I'm going to use a LG as a leaving group. So if you have with a poor leaving group, the SN2 reaction can happen because the nucleophile is strong enough to essentially cause the reaction to look for something that is positively charged carbon, and then make the leaving group, such as a chlorine or iodine. They can do that. Okay, so what about the base? Base is also, if it is a strong, they regardless of before they form actually leaving group, before leave, actually this is a very hot molecule trying to take the protons from the molecule, and then therefore it is also, we can say that this is a E2 mechanism. Okay, so E2 mechanism is going to be happen, and they are the one that is essentially, let's say we have a carbon here, and then hydrogen, and this is a leaving group, right? And then there are other bonds. So what's going to happen is, because of this leaving group, before they're ready to leave, despite whether it's a good or a poor, typically the poor leaving group, you have to use a very strong base to trigger the abstraction, and then therefore this one cause the double bond formation, and then the leaving group is leaving there. Okay, so that's a kind of the E2 mechanism, which is a series of reaction showing up there. Okay, but what about your base nucleophile is weak? Okay, so when your nucleophile is weak, you're going to have an SN1. They have to wait. I mean, in a way, I love to put it in. It has to wait. So what do you mean it? Is in here the nucleophile. So does here the base has to wait until the leaving group leaves and leave out of those. So that's why it is the first stage is leaving group has to leave, and that's the rate determining step. So the rate determining step is what they call unimolecular. So that's why it is something looks like that over there. So therefore, I can see that this one is more like an E2 reaction, E1 reaction, which is an elimination. So in this case, for what has to happen is leaving group, right? And here, and the leaving group has to leave first. And then they have made this carbocation. And then let's say there's a hydrogen. So this is the first step. And the second step is once you have a leaving group goes left, and the older base is weak, they love to take this one, and then they can form the double bond, and you ended up making the B with a protonated base. So that's the one. So in this cases, when you have a unimolecular, that's typically we are dealing with good leaving group. Okay, so that's the concept that I want you to keep in mind in learning about this, the nature of the leaving group, and that's why it's once again, because this is a good leaving group, and so that's a unimolecular. Okay, unimolecular. Okay, so I mean, as an extra time that I have given here, if you look at my video, if the question was asking that what about the E1 versus E2, the answer is it will be E1, and the product is, if you work on it, it will be like this, right? So once they left this one, right, and then you have a hydrogen. There's two hydrogen here, and the base will take it, and then this bond will form the double bond here. So therefore, you will have a base with a protonated base with cyclohexene. So the cyclohexene with a double bond, that's a product of a E1 mechanism. Okay, and the whole thing is because you have a very good leaving group. They don't mind to develop this carbocation, and that's the whole idea as a first step, and that's a rate determining step.